Okay, we're going to run through the questions for section 2. In this video, I'm going to cover only the questions that featured in week 1 of the prelim, and then the following video will be the remainder of the questions. I should apologise, it's very early in the morning when I'm recording this, so if my voice is not up to scratch, that is why. Anyway, let's just make a start. So hopefully you noticed that the questions in this paper, as opposed to the multiple choice, alternate between units. This isn't really standard for an advanced higher paper. Usually they are kind of chunked, so you'll get a load of unit 1 questions and then a load of unit 2 and so on. In this we decided to vary it up a bit just to keep you on your toes. So we'll be switching between units frequently. The first one is from unit 1. It's dealing with kinetics, and we've got to deal with some order of reaction content. So it starts off by describing some chlorine chemistry, and then features chlorine dioxide and how it's used in sterilisation, so just some kind of background and context for what we need to know. But what we really need to look at is the table of data that was obtained in a kinetic study. So what that means is they've taken a particular reaction, this one here, and they've played around with the concentration ratios of the featuring reactants. So there's 2 reactants, and they've taken each of these and they've varied the concentrations in a logical way to analyse the impact that has on the rate of the reaction overall. So for example, in the first experiment they've done 6 times 10 to the minus 2 moles per litre of the ClO2, and then 3 times 10 to the minus 2 of the OH minus ion, and they've found that that is the rate that they've produced. They've then repeated the experiment twice. Each time they've only made one change. They've made a change first of all to the ClO2 minus, ClO2, sorry, and then in the second case they've made a change to the OH minus, just so that they can see the direct impact that those changes are having on the rate overall, and we can use that. And that's the whole reason that this kind of reaction would be carried out. If we can see what the change is directly from one concentration on the rate, we can determine, okay, to what extent is that chemical impacting the overall rate in terms of orders of kinetics. So is it 0, first, second, third order, etc. Generally speaking, at this level, we're only dealing with 0, 1 or 2. So 0 order if it has no impact at all. First order if it's a linear impact. So if we double the concentration, the rate doubles, for example. And then second order if there's an exponential impact. So for example, if we double the concentration, the rate would then quadruple. So we're just going to take each one in turn, or we're going to choose useful ones to help us in that quest, and then see what the impact has been had on each one. That's what the first question is asking us to do, determine the order of reaction. So if you're given a question like that in a table, that is what you're expected to do. So for this first one here, I'm going to look for the change that was made to this chemical. So I'm going to take line 1 and line 2. So there's been no change to the OH minus, so I can ignore that. For the first one, for the first reactant that is, we've went from 6 times 10 to the minus 2 to 1.2 times 10 to the minus 1. This here is the same as saying 12 times 10 to the minus 2. I think this maybe tripped some people up, just that arithmetic there. So what we've done here is we went to go from here to here, we've doubled this concentration. So if we've doubled this, we should then have a look at the impact that that's had on this. If I run this difference through the calculator, I'll find that this second number here, 9.92 times 10 to the minus 2, is 4 times the amount of the initial value down here. So that suggests that if we double this concentration, the rate quadruples. And for that reason, the order of reaction for part A is second order. You could also have written just the number 2, that was accepted. I would rather that this was written. Alternatively, you could have written the reactant with the concentration square brackets, and they must be square with a squared above it, denoting that it's second order. But this is the best answer. Same again for OH minus. I'm now going to choose the second and third lines because these remain the same, whereas this gets changed. Now this one's interesting because it's not doubled it, it's tripled it. So I need to bear in mind what value I am looking for over here. I'm either looking for it to triple or I'm looking for it to triple and then triple again almost, right? So sort of exponentiate on itself. So I would either expect a difference of times by 3 or times by 9 in this case. And that will tell me if it's first order or second order. And I'm ruling out zero order because I can clearly see there has been a change, so it's not no impact. So if I've tripled here, I can actually see that this value is also triple this one. So for that reason, it's going to be first order kinetics with respect to the OH minus. Again, you could also write 1 or the square brackets OH minus with no number at the top, indicating that there would be a 1. Up to you. But you had to get both of those for individual marks for that question. So if we're then going to try and write the overall rate of reaction, I need to get the nomenclature right here. It's going to be rate equals lowercase k, which is really important. If we don't use this, the SQA do not award you a mark. A capital K or an unclear case does not get you the mark. The reason for this is because a capital K is used for the equilibrium constant, not the rate constant. So if there's any discrepancy over the casing that you've used for this, you're not going to get a mark. They're very strict when they're marking that kind of thing. So bear that in mind. And then we're going to multiply whatever that constant is by this value here to the power of 2. And we're going to multiply all of that by this value here to the power of 1. And that is my complete rate equation. Almost. What we're saying here is that the rate varies with this proportion squared and this quantity on its own, with some kind of constant k being involved to make it an equation. Without that constant, this would just be, well, the rate varies with these two things, but we want to quantify it. So that's where the k value comes in. And then we can now do a simple sort of workup to figure out exactly what k would be by taking one of the lines in one of these experiments. So we just choose one, it doesn't matter. They're all true, right? They all are accurate bits of data, so I could choose line 1, 2, or 3 to carry out the equation that I'm going to carry out. And to keep things simple, I usually just choose the first one. It's usually the simplest one numerically to work with, but it's also just the first one, so that's the one I'm going to use. And we substitute that into the equation that we've just formed. So we've just agreed that this is the rate equation, so I want to know what k is, and I know what this, and this is. I just need to then figure that out. You'll notice though, there are 2 marks for this. So I also need to calculate the value for the rate constant with the units as well. It says including appropriate units. So I'm going to do that at the site, just as an extra bit of analysis. So first of all, I'm going to rearrange my equation. So I want it to be k. I want to get rid of this stuff on the right hand side and put it over to the left. So it's going to be k is the rate divided by ClO2 squared times OH minus in square brackets. And then I'm choosing the rate from the first one, so that's going to be 2.48 times 10 to the minus 2. I'm going to divide that by 6 times 10 to the minus 2. But this value is squared, and that gets multiplied by 3 times 10 to the minus 2. So you can work that through, either putting that all into the calculator at once, which is risky, but if you use brackets properly, you can do that. Or I would advise that you do complicated values first and then expand out. So maybe work out this value individually, the squared term, and then multiply it by this, and then keeping that number in the calculator, type in that, divide it by your answer for this bottom line. Either way, it brings you at 230 or 230. So now what we need to do is think, okay, how do I get the units? Now you've got 2 options. You can just memorize what the units are depending on the overall order of reaction. So in this case, if we've got individually a second and a first, overall this would be third order. So I can just remember that the units for that are litres squared per square mole per second. Right, I can just have that sort of memorized and ready to go. Or you can do some analysis to figure out what that would be. So you're literally substituting in values from the headings of the units into this equation that you've just used. So we can do that sort of as a side step here. So that's what I'm going to do. So in the top line is my rate. So it's going to be moles per litre per second, and that is going to get divided by moles per litre, because that's a concentration value, but the first one is going to be squared, and I'll multiply that by a second moles per litre value. So if I follow that through, I will just do each step individually, so hopefully it's clear. The top line is going to stay the same here, because I'm going to sort of simplify and gather like terms on the denominator. So that's going to be moles squared to the square litre times moles on their own per litre. Again, on the bottom I can still sort of gather like terms there. So that stays on the top as is. And then I've actually got moles cubed per cubed litre. And that's all the sort of breaking out of brackets that I can do there. And now it's my job to sort of simplify by dividing the ratios that stay. So per second is on its own. There's nothing to cancel down there. I'm sort of working right to left here. Per litre on the top and per cubed litre on the bottom. So I can get rid of that one and I can reduce this number by 1. I can simplify down. Same deal with the moles. I can get rid of that one and reduce this number by 1. Now what I want to do is present this in a way that makes sense. So usually it's positive numbers followed by negative numbers in terms of powers, and I should do it in order of positivity. So positive numbers first, and also I should present it in a way where it's all ideally on one line. So if I've got per second divided by square moles per litre squared, that's not a neat way to represent that. So I'm going to flip the denominator numbers up to the top, and that will change the sign. That will change the sign of the power. So if it's negative, it becomes positive, and vice versa. So that means that instead of per square litre, I would have litres squared, and instead of moles squared, I'll have per square mole, like so, and then the per second stays where it is. And that's how we arrive at that second mark. Right. Again, if that is too much of a mathematical headache, just memorise them. There's a table for the 4 units of K that you would have to know. So for 0, first, second and third order, if you simply memorise them, then you don't have to figure that out. Question 2 is a lot shorter. It's unit 2, and it discusses a type of chemical called a paraben, and it gives a specific example of ethyl paraben. We'll not spend too long talking about that, because all it wants to do is ask you, state the type of hybridization which is adopted by the carbon atoms in the aromatic ring. So nice and quick, if we think about what the aromatic ring actually means, we've got a structure which is a hexagon like so, with a circle in the middle. That denotes that there are a delocalized system of 6 electrons, which usually are bonding via a pi bonding system, right? And we could technically argue for the Kekulé structure. So that's when we have alternating double and single bonds. In this context, it's maybe more useful to think of it for the second structure here, because that will force us to remember that there is a double bond featuring on each individual carbon. And in order to be able to do that, each carbon is going to have to leave out a p orbital free from the hybrid set in order to make that happen. So for each of these, the maximum possible hybrid orbitals that we have is 1s contributing, and then out of the 3p orbitals that are available, one of them has to be left out to do this. So that leaves us with 2p orbitals. So overall then, that's 3 orbitals. So I would have sp2 hybridization, and there would be 3 of these, and then the 4th orbital would just be a standalone p orbital. But what it wants to know is the hybrid, the type of hybrid orbitals that would be formed. So it would be 3 lots of sp2. Okay. The way to think about that, and the way that I just did that, is to assume that the maximum possible contribution of all 4 outer electron orbitals of carbon forms the sp3 hybrid set, 4 of these. And then anytime you need a higher order of bond, a double bond, a triple bond, you need to remove a p orbital from this set respectively to be able to do those. So if it's all single bonds, sp3. If you need a double bond, it's sp2 and a p left over for that double bond. If you need a triple bond, it's sp and 2 individual p's left over to do each pi orbital interaction for each of the bonds in the triple bond that aren't a sigma interaction. Either case, sp2 is the answer for question 2. Question 3 is using your knowledge. I'm going to discuss these separately at another time rather than use this video, which I want to be more of a walkthrough. Obviously, using your knowledge questions or open-ended questions are a bit more interpretive. There's definitely more than one correct variation of the answer, so I don't want to be too prescriptive in this walkthrough. Question 4, so back to Unit 2. Page 8, which we're looking at now, is all instructions. There are no questions featuring yet because it gives us a scheme of reaction steps that are used in the artificial synthesis of adrenaline. So we've got 3 steps and there's something different going on at each one. And we're given the target compound at the top in case we need to do any analysis of that. But then we're mainly going to be focused on what are the types of reactions and what reagents would we need to cover each of these 3 steps. So I'll reference these as we go through. So if we turn over the page, first part A has 4 parts. Firstly, it's asking us to suggest the type of chemical reaction taking place in step 1. So straight away, what should have jumped out at you? Well, 2 things arguably, but the first one mainly would be we have a benzene ring here, which is substituted by 2 hydroxyl. So technically, it's a phenol type compound, but in either case, we substitute something directly onto that benzene ring. The only time we've seen that in terms of reaction types would be electrophilic substitution. And therefore, that's the answer for the first question. The other thing that might have jumped out at you is you might not have recognised this as a functional group that we've worked with. And that is true. We haven't done that. We haven't looked at this carbonyl with a chlorine directly attached to it. But you don't need to know the specific chemistry, the specific mechanism by which this attaches to this. You just need to know that that is what is happening. You've got a carbon here that's forming a bond with that carbon there, which is an aromatic ring. And your only possibility to do that is to substitute electrophilically. So electrophilic substitution, or simply just substitution, would be the answer here. As long as you don't state nucleophilic substitution, which would be a cancelling error at that point. Part 2, the aromatic product formed in step 2, even though there's only one product, I don't know why it's specified, but there we go, contains an amine functional group. State the type. So whenever it's asking for type of amine, it's asking for primary, secondary or tertiary. In this case, we've only got 1 hydrogen, so there's 2 points of substitution onto the nitrogen, 2 carbons, so in that case it's going to be a secondary. Just to be clear there, for that answer, I've written 2 with a little degrees symbol. I would rather you just wrote the full word, secondary, primary, tertiary, whatever it is, but that is technically acceptable. Okay, just to be clear in what I actually wrote there. Moving on to the next part, name reagent X used in step 3. Now to do the reaction in step 3, we're looking at moving from the carbon to oxygen double bond here to a carbon to oxygen single bond with a hydrogen. So straight away my instinct there was, before I'm starting to think about reagents and before I'm even starting to identify the reaction type, I'm looking to see what has changed from this molecule to this molecule, because actually the answer is not very much. We've just went from this functional group to this one. Everything else is the same, and that's often how these big workup experiments are performed. We just make small changes, one thing at a time, until we end up with the product that we're targeting. So in this case, we went from a ketone to a secondary alcohol, and that's an example of a reduction reaction. We mentioned this in the multiple choice paper. So X, the reagent required here, would be the only reducing agent that you need to remember from the course, which you can name, or you can write the formula of. It's lithium aluminium hydride, written like that. Okay, if you do specify the formula, obviously the formula does need to be correct. If not, you can just write it. And then lastly, part 4, identify the steps in which the product has a carbon chiral center. So we're looking for 2 things. We're looking for a fully substituted carbon, so no double bonds. We're looking for 4 individual groups, and they all have to be different. Now, when we say all have to be different, it means we're looking at the entirety of each of the substitutions onto one carbon, not just the direct neighbour on that atom. I'll explain what I mean now. So the answer is in fact that carbon there. Why? Because it has 1, 2, 3, 4 substitutions onto it. It's fully saturated. And what I don't want people falling into the trap of is thinking, well, okay, there's an oxygen here, a hydrogen here, but then there's 2 carbons. Therefore, it's the same. You need to look at the entirety of the substitution. So all of this, okay, has to be completely different from all of this. Now, even if there was a difference of 1 atom, that would be included in being considered a chirocarbon for that centre, right? It has to be, if it's not going to be included, it has to be completely symmetrical. So, for example, a molecule, if we look at one like this, okay, both sides of that line that I've just drawn are completely identical, right? If there was even one slight change, that wouldn't be considered identical. That's the kind of analysis that you're looking to perform. So, for the chiral centre, then you're indicating it with a little asterisk usually. So that there. But in this question, it just asks you to identify the steps in which the product has a chiral centre. So the answer for this one simply is just step 3. I think even the number 3 alone written down would be acceptable, as long as you get the step right. Okay. Now for part B and part C, this is very much Unit 3, tying into Unit 2 here. Some chemical analysis that we're doing on the adrenaline, how we would work up, maybe testing the purity or having a look at dosages that are administered in treatment. And that is what the first one is tackling here. So for part B, adrenaline is used as a treatment for severe allergic reactions. A typical dose contains 0.3 centimetres cubed of 500 parts per million solution. Calculate the mass delivered in one dose, and it wants it in milligrams specifically. So 2 things to point out. The first thing is actually the last sentence here. So it specifies the unit. If you give a correct answer in a different unit, you will not get the mark awarded for that question. If it does prescribe the unit that you need to use, you must follow that. And that does make sense. If we were working in a sort of medical environment here, and there was a specific unit prescribed, then that's the unit we would be expected to work in. Even if the answer often might not make sense, but for our purposes, it will usually fall within an acceptable range of significance or number of zeros or whatever it is for the unit specified. So it says milligrams and you write something else, you're not going to get the mark, even if that answer is equivalent or correct. The second thing is we need to remember what ppm means. So ppm is unitless and it's used to apply to various unit situations so we can adapt it to our needs. So parts per million is a way of signifying a very small quantity or a very small concentration almost within a larger quantity. So the most common for this are millilitres in a litre or milligrams in a litre or milligrams in a kilogram, whatever is more appropriate. It's just a way of referencing a very small quantity to a quantity that is 1,000,000 times bigger than it, which is why it's parts per million. For this context, we're obviously dealing with a dosage that is a solution. So we're given a volume. So the one that we're going to be using is the millilitres one. So what we are told here is that for every litre, we are working with a much smaller quantity. And I've actually said that wrong. That's not the equivalent that we're dealing with here. So we're wanting to go one smaller than that to make that true. I've simply went by an order of 1,000 there in that first example, whereas I've went an order of 1,000,000 in the second one. So we actually want to go to the next one down. In any case, we will find that we have 500 of that smaller unit within our litre, which gives us the equivalent of 0.05 millilitres. And then to scale that to let's scratch that. See, mistakes in real time here. The appropriate choice is actually the milligrams in a litre because of course we're already given the volume. So I was approaching this from the wrong direction, so you can ignore that. So if we work with milligrams in a litre, what we are told is that we have 500 of those in a litre. Just ignore that top part. And we want to convert that into something more useful. So if we have 500 milligrams and we want really to be finding out about how much of this lies within this, we need to change this to something a little bit more useful. So in this case, that would be that would simply be grams. So if we're going from 500 milligrams and we want to convert into grams, we need to divide that value by 1,000. So we end up with 0.05 grams in 1 litre. And then we want to know, okay, how much is contained within 0.3 centimetres cubed. So then we can play around with this unit, right? So instead of saying grams in a litre, it might be more useful for us to directly convert to centimetres cubed. So 0.05 milligrams in 1 centimetre cubed, for example. And then we can go from there, and if we have... I actually think I've ended up down a bit of a rabbit hole here. I'm going to start this one again. Now, I'm keeping this in the video because I guess it shows you that this can be confusing. So I'm going to show you another way to lay this out. And this is how, if I was not recording a video and I was getting confused, I would take myself aside, and this is how I would work this out. I was trying to be fly there and do it in my head, but I've ended up making a mistake, and that might well happen to you. So let's do it properly, basically, is what I'm saying. So let's specify what this unit means. So 1 part per million is equivalent to 1 milligram per litre. Okay, so if we're told we have 500 parts per million, that's equivalent to 500 milligrams per litre. Now, since 1 litre is 1,000 centimetres cubed, and this is represented as 500 milligrams in that 1,000 centimetres cubed, we can divide both sides by 1,000 to represent this litre quantity in centimetres cubed. So that means if we divide both sides, 0.5 milligrams is contained per centimetre cubed. That's a bit better than what I ended up with over on the right hand side. So this is where we need to be. So I would encourage you to do it that way. Maybe just very clearly write out in the first instance what that means, and then whittle it down as you go. I was trying to be smart on the right hand side here. Okay, so we've now got it per centimetres cubed. Right? So to do this in full, 0.5 milligrams is contained within one of those centimetres cubed. We want to know how much is contained within 0.3. I mean, there's nothing stopping you sort of dividing that number by 10 and then timesing it by 3 to get that number x. But again, I just want to show this in full. So that implies that to get x, we need to do 0.3 times 0.5 and divide that by 1, which is what I'm going to do now, which lands us at 0.15 milligrams. So not as complicated as I made out on the right hand side. Now, interestingly, the marking scheme actually says 0.2 milligrams. And the reason that they've included that as an appropriate answer is because our lowest level of significance in the question is 1. In fact, both of these values have different numbers of significant figures to our final answer here. But this is also an accepted answer for 2 reasons. One, using these quantities, this technically could be considered an exact answer, but secondly, it's within the acceptable range of significance. So remember, we're allowed 2 above and 1 below in terms of numbers of significant figures. But technically the lowest level of accuracy here is 1, as opposed to this value which has 3 significant figures. So we really should be writing our answer to 1 significant figure, which would be 0.2. I'm going to keep it at 0.15 just so that I can move on from this question. Okay, part C is about TLC. Now, to be honest, this is a higher piece of content. It's been asked at Advanced Higher because it features as something that you should be able to carry out as an analytical technique in the practicals. But these analytical techniques that you looked at in higher, volumetric analysis included, obviously do come back up at this level, so it's expected prerequisite knowledge not just for the project, but for past paper question content as well, and exam content. So we can extract it in terms of adrenaline. We can run a TLC plate, a thin layer chromatography plate. You've just to complete the diagram and label it to show how this should be set up and compare the extracted adrenaline with a sample of pure adrenaline. So you've got a couple of clues in the question here. You've obviously been given a template of the diagram, you've not had to draw it yourself. Clearly indicates that the solvent plate, or the TLC plate, sorry, so that could be simply a piece of chromatography paper, it could be something a bit more high tech, it could be a plate, which is like a sort of plastic material with a coating, which is a bit more absorbent and a bit more reliable, a bit more hard wearing as well. In any case, that's added to this solvent layer, and you're expected to show how to run this. So as a bit of a reminder then, you would pencil in a straight line using a ruler, which you should use to draw that line, by the way, that must be above the solvent line, because you're going to spot two solutions. You're going to have the extracted adrenaline sample and a sample of pure adrenaline. So you're going to have your sample, and you're going to have the pure sample here. Now, just to confirm, the marking scheme states the diagram must show labelled start positions, e.g. spots, crosses or letters, of the extract and pure on a horizontal line above the level of the solvent. Obviously, if you spot solutions onto a piece of paper and you draw that line so that it's underneath the solvent, that stuff will just get dissolved in the solvent. So it must be sitting above that solvent line. Otherwise, this is basically just like putting a bit of paper in a beaker of water. It's all just going to run off. What we want to do is have the solvent, obviously when you add this piece of paper to the solvent will gradually run up the paper. And as it does so, we'll eventually make contact with this line of solvent spots, and it will drag them up the plate, probably to varying heights, because the extracted solution won't be the exact same concentration or makeup as the pure sample, so it might be slightly different heights, but we could compare those heights and compare therefore the RF values at that point, and that's why we're running this. So basically, don't draw your line underneath the solvent line, otherwise that would be silly. And then you're obviously expected to label these, so you could simply write extract and pure. You could draw arrows pointing to those things, but in real terms you would draw it onto the TLC plate directly, so there's nothing stopping you writing that on there, as long as it's underneath the spots, and that would be written in pencil, of course. Cool. Moving on. Question 5 puts us back to some equilibrium stuff, which hasn't come up since multiple choice. Unit 1 features quite heavily in this first half, which may have added to people's enjoyment or difficulty, depending on your stance on that. But in any case, phosphorus forms different compounds with chlorine. When heated, phosphorus pentachloride dissociates to form phosphorus trichloride and chlorine. So it gives us this equilibrium equation with a delta H at the side again. Now in this case, we actually don't need the delta H at the side. This could come up in a future topic. You might have to use this to work something out, but in this case we don't actually need it. It's just there to suggest that this is an endothermic reaction, which we also don't need for this reaction. In an experiment to determine the equilibrium constant, capital K, 0.1 moles of PCl5 was placed in a sealed 1 litre flask and heated to 250. At this point, it's important to mention both the number of moles and the volume, because if the volume is 1 litre and the quantity we're measuring is moles, we're measuring in moles per litre, so we're effectively able to use this molar quantity as a concentration, because it's a number of moles contained within a litre flask, and that is moles per litre, which is our concentration unit. So that gives us permission to sort of do the equation and the calculations that we're about to do. At equilibrium, 0.042 moles of PCl3 had formed, therefore calculate K. So we're going to launch into our Rice method for this one, and we're going to see where that takes us, but I'm going to do a slight variation of that method. Reason being, we've got 2 products going back to 1 reactant, and I don't want anyone to get mathematically confused about how mole ratios work. It's not necessarily always something that's directly quantitative on both sides in terms of losses and gains. It's a ratio. And I'm just mentioning that now so as that there's no confusion as we go through this calculation. So anyway, we're going to set up the balanced equation, which I know it's written above, but I like to write it in so as that I can work underneath these chemicals. I find that that makes things much easier. And then we're going to plot out our Rice calculation, like that. So we've got a ratio, nice easy one, 1 to 1 to 1. We have our initial numbers of moles, or concentrations in this case, they're interchangeable, 0.100, and obviously initially we've not done the reaction, so there's no quantities of either product on the right hand side. And then the last piece of information we have is at equilibrium there's 0.042 moles of PCl3, so we can go right over here and write that in. Now if it's 1 to 1, we can also justify that we have the same number of moles or the same concentration of chlorine gas on the right hand side as well, and we can therefore say, okay, we have gained this X value. Right. Now, why am I using an X? I'm using an X to write a simplified expression for the change on the left hand side, because I don't want people getting muddled up with quantitative amounts versus ratio amounts. In other words, what I'm saying is I don't want to remove this quantity twice in the change column or the change row for the reactant. Simply saying if it's 1 to 1 to 1, I need to remove this quantity from this because it's a 1 to 1 ratio, right? So what I mean by that is the change would be our initial value 0.100, subtract this change. What is this change? Well, X is equal clearly to 0.042. So on the left hand side, my moles at equilibrium of the reactant would be 0.100 minus 0.042, and that brings me out 0.058. That's important because I don't want to accidentally remove a second quantity of that, right? I'm not doing this twice, it's 1 to 1. So you base it on the ratio, not the number of products that you have, because arguably you could have, I don't know, this could be a reaction where something degradates and splits into 3 or 4 different products. You wouldn't then subtract 3 or 4 versions of that ratio. That's not how that works. You would end up with a negative number over here. Okay. So I've kind of ran out of space to do my actual calculation here, but what I need to do is substitute this into a workable equation that I can actually use to work this out. So at this point though, I do have a couple of marks. Well, I've got 1 mark, right? And working this number out, I've gained 1 of these 3 marks. What I now need to do is evidence, okay, how do I actually work this out? So to work out K, remembering that for the equilibrium constant, it is the concentration of the products, must use square brackets for this, and any powers for the ratio, which we don't have, so they're all to the power of 1, divided by the same thing for the left hand side, so the concentration of the reactants. Again, the power value, the superscript would be any numbers in the mole ratio, but we don't have any to use here, so it's just as is. So if we work this through and substitute the values that I've just found for the number of moles at equilibrium, it's going to be 0.042 times 0.042 divided by the number I've just found, 0.058. Now I can gather sort of like terms, I can simplify this down a little bit and say that on the top then, because those numbers are the same and they are a product, 0.042 squared divided by 0.058. And when you work that through, the number you should generate is 0.0304, written beautifully at the side there. Okay, so just to be clear then, your second and third mark, but your 3 marks really come from the generation of the final answer, but you can get 2 marks for that statement alone because you've demonstrated that you know how to arrange the numbers and that you've got the 0.058 in there. So your numbers come from working this number out, substituting correctly with the right number of terms and the right positions, and then the correct final answer. Okay, secondly, the temperature of equilibrium was increased to 400. Explain the effect of this change in temperature on the value of the equilibrium constant. I would argue this is a very easy 2 marks to obtain. Okay. You need to make 2 statements. You need to say something about the forward reaction being favoured, or more products being formed or less reactants being formed. Or your classic statement from higher, which would be equilibrium shifts to the right. Any one of those statements would get you 1 mark, but then you need to just relate that to the effect numerically that has on the equilibrium constant. So up until that point, really all I've said is a higher level answer. To make it advanced higher level, you would say something like the forward reaction is favoured, or the equilibrium shifts to the right, therefore K increases. And that's it. That's how you get that 2nd mark. Nice and easy. Moving on. For part B of this question, we're technically asked to do a bit of VS EPR here. We could kind of do this on the fly, to be honest, because of how substituted the phosphorus becomes in this question. But let's just read through it. It says, the 3-dimensional structure for the PCl4 plus ion is shown. Complete the table for the PCl6 negative ion. The fact that there's 6 of them, we only know one shape variation at advanced higher level that fits 6 ligands onto a central thing. It's octahedral. And that is the correct answer here. And if you include the charge properly, you could probably have generated that answer very quickly. In this, I'm going to show you how we arrive at that answer technically, but I'm going to do some VS EPR. So just as a reminder, for valence shell electron repulsion, we're doing the central atom and how many valence electrons that contributes. Phosphorus is in group 5, so that's 5 electrons. For each ligand, we count 1 electron, so we get 6 chlorines, 6 electrons. We've got a negative charge, so it's an extra electron. So if I total these up, it's 12. And then if I divide that by 2 to get the number of pairs, that's 6 electron pairs. And they are all bonding pairs. Why? Because this number matches the number of substituted atoms or ions or ligands that I have. So there are no lone pairs in this situation. And if there's 6, I can say that it's octahedral. And that's where that comes from. So it's going to be P in the middle drawn with 2 straight lines above and below. Now I need to show the correct coordination geometry here. So I need to have 2 pointing back with their dotted or dashed lines there. And then I need to have 2 pointing forwards. They need to be the wedged lines. Doesn't need to be the neatest thing in the world. However, they need to be in the correct places. There are slight variations you're allowed, but most you're not. So please just draw that accurately. Getting in the CLs around the sides. And I'm not quite finished at this point. I need to show the charge. So overall, the entirety of this is a negative ion. So I need to show that in square brackets with a negative charge at the top to get that mark. Okay, so for question 6, we've got a mixture of some analytical techniques, talking through some processes, and then a calculation that is actually heavily based in higher content, which, as I've said, does come up, especially for Unit 3, having a strong background for higher percentage yield, atom economy, that kind of thing. Reactants in excess is very important, as well as the practical stuff as well. Okay, so for 6A, phenolphthalein is an indicator that can be prepared by the reaction of phenol with phthalic anhydride. It can be prepared by this method, and then it discusses how recrystallization is important in this preparation. You have then to outline the steps that should be carried out to recrystallize the phenolphthalein. You've got to mention 4 things explicitly to get the 2 marks. For each one you miss, you lose a mark. So you're only really allowed to miss 1 to get 1 mark. First thing, you need to mention that it is a minimum or a small volume of the impurity in soluble solution and soluble product, whatever it is that you're using. Secondly, you need to mention that hot solvent or heating should take place, or hot ethanol or hot aqueous ethanol or whatever should be used to make the solution, to dissolve it. This must be followed by filtering, right, to remove impurities. You could say that, but really it's just wanting what should be carried out. So if you just said filter it, that would also be fine. And lastly, you need to cool it. Now, particularly for these last 3, they need to be in the right order. You can't say that you're going to filter it and then heat it and then cool it. You won't get the mark for that. It needs to be logical. So you need to dissolve a minimal volume in hot solvent, filter it, and then cool it. otherwise you don't get the mark. Now, for naming a technique that could be used to determine if this is a pure sample, so another purity check, you've got a few. You can mention melting point or mixed melting point analysis. You don't need the word analysis after it. IR, or infrared spectroscopy, which is the letters IR, would simply work. NMR, mass spec, you could even write MS, that is acceptable according to the marking scheme. And then we've just seen one on a previous page. You could also have mentioned chromatography or TLC. Any purity check analytical technique would be appropriate here. Boiling point would not be acceptable. You can't analyse the boiling point because we're dealing with something that goes from a solid to a solution. So we're not boiling this. That's not something that we can check in the literature. But any of those that I mentioned, so that was what, 1, 2, 3, 4, was five answers that you could have given there. Any would be acceptable. Now, part B is a bit more involved, but a lot of it is from higher. Right? So we're going to read through this question and then I'm going to lay it out in a hopefully more logical way than I did the PPM question. The equation for the reaction is given below. So we've got phenol mixing with phthalic anhydride. We're making the phenolphthalein and we've got a byproduct of water. We're told 2 quantities for each of the reactants. Straight away, that line indicates to me that this is a reactants in excess question because I don't know which one of these is the limiting reactant. That's an instinct that you should still have from higher. If you don't, well, make sure you have it now. If you're given 2 quantities, it could be 2 masses like this. It could be a mass and a volume and a concentration for the other one. It could be a mass and a volume and a molar volume. In any case, it will be 2 separate quantities that you can get 2 numbers of moles from. And then you need to play that game of figuring out which one's the limiting reactant and which one is in excess. Because if you carry through the wrong number, you're going to lose at least a mark because you've based it on the wrong thing. So that's the first thing to point out. So we're going to do that first. Let's just do that actually before we go any further because we know that that's what we're coming up against. So let's just call phenol thing 1 and we'll call it phthalic anhydride compound 2, just to make this easier. So for number 1, I'm going to work out the number of moles by doing the mass divided by the GFM. So that's going to be 0.96 divided by 94. And then for the second one, I'm going to do the exact same thing. It's going to be 1.05 from the question there, divided by 148. At this point, it is extremely important that I bring attention to this. The majority of marks, when I'm marking this, are usually lost for a poor recording of the significant figures or rounding in this part of the question. Unless it's a final answer, keep accuracy in the question. If you need to regenerate a number to put it back into your calculator later on in the calculation, then do that. But for now, we're just going to record it as accurately as we can, as a placeholder almost. So 0.96 divided by 94 gives me this big string of numbers here. I am not rounding that to 0.01, otherwise my answer later on will be wrong, because then you're carrying through a lot of inaccuracy in the question. Okay, so we need to keep the number accurate as we move through. So I'm going to leave that there. For now, I'm just going to write 0.01021 ... I know that means, okay, there's a higher level of accuracy required for that number there, which I can go back to. I'm going to do the exact same thing for the other side. 1.05 divided by 148 gives me 7.09459, just rounding it there slightly, times 10 to the minus 3. I can leave that there for now. Not got a mark yet. I've not really done anything with these numbers. I've just worked out 2 numbers of moles, so I'm not really demonstrating any knowledge here. What I can now do though is identify a limiting reactant. So what I can say is, I can check my equation, it's 2 moles of these required for every 1 mole of this, right? So to determine limiting reactant, I can say it's 2 to 1. Therefore, if I try to use all of reactant 1, I'm going to see what happens with reactant 2. So if I substitute in my 0.01021, etc., I'm now going to go back to my calculator. I'm going to redo that calculation, just so I've got that number to hand again, the exact number, if it wasn't saved in your calculator, and I'm going to divide it by 2 because it's a 2 to 1 ratio. So divide by 2, and that gives me this number here. So 5.1-ish. Let's call it 5.11 times 10 to the minus 3 needed. Now what I've written there is, I'm saying, okay, if I try to use all of reactant 1, this is how much of reactant 2 I will need, because it's a 2 to 1 ratio. Can I perform this? The answer is yes, I can, because this number here, which is what is required based on this, is less than the total that I have available. This is my sort of 2 banks of available solution. So because this is higher than this is my limiting reactant. And you can communicate that clearly in your working if you like. For now, I'm just going to circle this. This is the one that we need to use. This is the one that we need to ignore. This chemical here, because there's a majority of it based on the ratio, is in excess. So we don't need to really think about it from this point forward. What I do need to do is use this value going forward to figure something else out. And that's all I need to take really from these first numbers here. So if we read on, in an experimental procedure, the percentage yield of the product is 58%. So I'm going to stop again. If it's talking about percentage yield, I'm going to need a theoretical yield at some point. So that's the next thing that we're going to calculate. So in order to do that, I need to show an understanding of what chemicals are going to be involved in working that out. I know that this is my limiting reactant. So all calculations are going to be based on this thing. And we're going from here to here. That's my product. So I want to know, theoretically, if I used all of my available quantity of phenol, which is my limiting reactant, how much phenolphthalein would I expect at a 100% yield? That's what I'm going to figure out now. So the ratio is, again, 2 to 1. 2 to 1. Just happens to be the same ratio, but evidence that again. So you just write down all the important bits of information. I can then substitute in the GFMs that are involved. So it's going to be 2 times 94 goes to 1 times 318, because I need to include the mole ratio in this, what I'm going to do as a sort of proportion calculation. And that's saying, okay, if I have, let's just run that quickly, 2 times 94, 188. If I have 188, I will make 318 grams in theory. I don't have that quantity though, right? What I have here is a molar quantity, but I'm going to go back to the original mass quantity that was given in the question. So I'm saying, okay, if I have 0.96 grams, therefore, how many grams of phenolphthalein can I expect to produce? And then it's just a simple proportion. So 0.96 times 318 divided by 188. I've got 188 in the calculator there, so I can do this quickly by just typing 0.96 times by 318. Now, in terms of the sort of hierarchy of operations, I don't really need the brackets here, but I'm just going to stick it in anyway. So that gives us 1.62383. That's enough rounding for that one, probably. Okay, so this here is my theoretical yield. You do earn a mark for that according to the marking scheme. And the idea of this one being in excess, clearly evidenced, and then you using this number later on, if you do carry that number forward later on, would gain you a mark. The evidence alone of the idea of excess is a bit iffy. It really would have to be very clearly written, that was what you were doing, but it would cement you earning the mark if you then say, like I've circled this number, if you then use that later on in the calculation, or select that chemical later on in the calculation, then that would evidence that you've known the excess principle as well. So we're kind of potentially looking at 2 marks here. So I've got my theoretical yield based on my limiting reactant. I have got a percentage that was obtained, and I want to know the mass that was produced in grams. So what I'm really gunning for here is the actual yield that was produced in this process. So what I have is percentage is equal to actual yield divided by the theoretical yield times 100. I don't want the percentage though, I've already got that. So I'm going to rearrange this equation to say it should be the percentage divided by 100 times by theoretical yield, I'm just moving things around, equals the actual. So if I substitute those things in, it will be 58 divided by 100 times our theoretical 1.623 blah blah blah, and I'm not even bothering to write it down because I have it in the calculator. I'm going to times that by 0.58, which is just the scalar that I get from here. And the answer gives 0.94 and a string of numbers. This is the point where it's important to consider significant figures. So having a look at all the data that we've got in front of us, just want you to have a think before I reveal what the answer is. What is the correct number of significant figures? Have I got that right straight away? Do I need to amend that at all? What would be the other acceptable answers in the marking scheme? Because there are another 3. Okay, I can reveal that this would be the bang on answer. Okay, now why is that? If I look at all of the data in the question, there's a lot of it. There's 4 GFMs, there are 2 masses, and there's a percentage. That's 7 values. I can rule out the GFMs. These are exactly known quantities or literature values because they come from the literature, the data book. So they are considered to be exact quantities. They're exactly known if they're referenced in a question. So I can ignore those when I'm making these considerations. That will make life easier, particularly when you're dealing with, say, something that's got 2 and something that's got 3 significant figures technically. Technically, these have got loads of significant figures because they're exact values. So I need to make my decision based off of this and this and this. If you're not being careful, you might just see this, think 1, 2, 3, and assume that the answer is 3 significant figures, but the lowest level of accuracy is 2, both in this case and in the case of the percentage as well. So I should really only quote my answer to 2 significant figures, 0.94 grams, and that's the exact answer in the marking scheme. 1 below, so 0.9, and 2 above would be acceptable. It's just important to think about rounding for each of those. So if I go to my number, 0.94, if I wanted to give a third, I would have to round that to a 2, so 0.942 would be acceptable, or 0.9418, and 8 would stay because there's a 2 after it. So it's important that whatever significant figure you're given, you do round for the last figure that you are quoting. So if the last figure needs rounded up, then you would round it, for example, given the 0.942. But if you're bang on the money, 0.94 is the correct answer for the third mark. Okay, to finish off, question 7. Reaction kinetics can be used to determine the order and mechanism of chemical reactions. Okay, we're then given 3 steps, one of which is slow, which kind of indicates that this is going to be an order-based question, a rate equation question. And we've got 2 fast steps as well, which we can essentially ignore for this first question because it's asking us to determine the overall order of reaction for the mechanism above. We're only interested in the slow, what we would describe as bottlenecking steps in a reaction to determine the overall order. If it's fast, it doesn't really contribute to the order of reaction that we've got going on. So we look at the slow step, we ask how many reactants are involved in the slow step. Well, there's 2, and we assume that both are involved. We would have to do a full kinetic study to actually confirm that with our little table, and we would sort all of that out. But for this purpose, if we're given slow, fast, fast, we assume everything is involved from the slow step. So that's first order with respect to each one. So overall, it would be a second order equation for that one. For part 2, write the rate equation of this reaction, where we're basing it off of both of those reactants. So very similar to our initial question, the rate is going to be equal to lowercase k multiplied by the concentration of peroxide, which itself is multiplied by the concentration of the iodide ion. So those 2 things there. And then lastly, write a balanced equation for the overall reaction. So for this step, you are just combining and cancelling. You're looking at what you start with, you're looking at what you end up with, and you're sort of overlapping things that are involved both as the products of one reaction and the reactants of the following reaction, and cancelling down what you make and what you produce at each stage. Now, there are a few ways that you can do this. You can map this out fully and, you know, sort of overlap what would be from a previous product and then included as a following reactant, and you can sort of overlap things and do the full working for that. I'm just going to sort of talk through this, and if that's still not making sense, I would encourage you to write it out in full until you get the right answer. Right? What we're saying is, at each step, are we adding on to a bank of things that we've already got, or are we subtracting from that? So remains to be said, right? Write a balance equation for the overall reaction. So our starting reactants at least are going to be those two because they're featuring at the start. We're then saying we make intermediately IO minus and H2O. But we then, in the second step, react our IO minus and it goes away. So what I'm saying there basically is I can get rid of that because of that reason. I briefly made it, but then in step 2, it features and then is changed to something else. So far, it's not looking like I've used my water in my second step, so that stays. H3O plus is introduced, okay? And for that reason, it's included in part of the overall reaction. And I generate HLO and H2O. So for now, they are now included on the right-hand side. However, in the third step, I use HLO, or HIO, sorry, and it doesn't appear again in the product, so they get removed. Okay, I'm adding on some more H3O plus, so that does stay, and I'm adding on even more I minus, and I generate I2 and 2 lots of water. So now it's just a case of sort of parsing out what I'm actually left with as a reactant and what was being used in the process of making this stuff. So I definitely have made, because the final arrow is here, definitely made this and made this. If I then look back, are there things that have been used as only reactants overall? Yes, right? It's this and this in brackets, so 2 lots of H3O plus, okay, as well as the initial peroxide and iodide. The waters that have been generated in both instances have not then been used again as reactants, so these are also featured on the product side as well. So then I'm just going to write overall what that leaves me with. So I've got H2O2, I've got not just the 1, but the 2 iodides, because I've added that on in the last step, I've added in some more. I've also got the 2 lots of hydronium. And then on the product side, I have generated an I2 molecule. And not just the 2 waters, but I've got these remainder waters from earlier on as well. So I've actually got 4 waters to end the process.